So some sequences that we have seen before, one that we've studied arithmetic sequences. We've also studied geometric sequences, and in particular, we're going to focus. We want to know something about the series as well, or the sum of those sequences. So this is an infinite. This is a geometric sequence. It's going down by half. So it goes half times a half times a half times a half times a half, and we're just going to get half, 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 half. So the properties of this is an infinite geometric series. The sum of all these terms always has a finite sum. Okay, and we can just kind of show that in this example here, is because imagine us shading each term of this sequence. Okay, our first term is 1/2, we shade that. Okay, the next term is 1/4, we shade that. Next term is 1/8, we shade that. 1/16, 1/32, 1/64, 1/128, etc. And we're always going to be shading half of what's left over. And so we'll never actually get to fill up the rest of this square. So the limit as this goes to infinity is going to be just this one whole square. So the sum of this infinite series ends up being, in this one in particular, the sum of this infinite series equals 1. Okay, this is what we call a converging series. So I'm going to start introducing slowly some terminology, and this terminology is very important to what we're going to be doing later on. So this idea of convergence, this infinite series converges. Okay, it converges to a finite sum. So that's what it means when I say converging. If we take a look at this sequence here, notice that the infinite geometric series goes down to 0 very quickly. Okay, so that's why it gives us a reason why this sum has a finite sum, because its infinite pieces are really, really infinitesimally small. So they end up adding up to a finite sum. Although we're adding zeros here, okay, an infinite number of zeros, the infinite zeros gives us a finite sum. But there are other sequences which that doesn't hold true. So we take a look at a harmonic series. Our harmonic series comes from the harmonic sequence, and there's very interesting things about the harmonic sequence. And this one actually is one that we will use. The natural property of this sequence is very useful to us in calculus. So the harmonic series is just basically we go 1, 1/2, 1/3, 1/4, etc. And it's to do with, it's called the harmonic series because I think it was Pythagoras who realized that when you vibrate any object, okay, of any length, it creates some sound. And if we have the vibration lengths, in these harmonic, in this type of sequence, we end up with a certain type of harmonic. Okay? These are resonant harmonics, which are naturally will resonate with each other. Okay? So if we have a length of 1, it makes some kind of sound. Length of 1/2, it makes a very similar sound. And 1/3, 1/4, 1/5, 1/6, 1/7, these will all end up resonating with each other. Okay, so this is what I've kind of shown here. And those of you who know a little bit about physics understand that these nodes, because they match, they will end up being in phase with each other, and they resonate with each other. Okay, they make each other will move. Each of these vibrations will actually interact with the other vibrations. Okay. So this sequence is called the harmonic sequence, and it goes down like this. And this one, obviously, if we let this go to infinity, 1 divided by infinity is 0. Okay, which we're essentially adding 0 at the end. But this one, for whatever reason, well, it's not whatever reason, but this one has an infinite sum. So this one, always the geometric series, always has a finite sum. The harmonic series has an infinite sum. Okay, so we'll just even write it down because this is something that's important. The harmonic series has an infinite sum. And if we actually compare the two graphs, you can kind of see that one goes down to 0 very quickly. The harmonic series does not go down to 0 very quickly. So although we're adding zeros at the end, we're adding bigger zeros essentially and an infinite number of them, which happens to just end up giving us this infinite sum. Okay? And this is actually the boundary series of that. Okay? So we shouldn't be too surprised by this, because when we integrated these unbounded regions, sometimes we ended up with infinite sums, okay, so infinite areas when we integrated these, and sometimes we ended up with finite areas when we integrated these. So this shouldn't be too much surprise that we get some as finite sums, like it's above, and these infinite sums that we have here.